Acid and base reactions. All right, so ascorbic acid in citruses, we're seeing here. We need to know some of the properties of acids and bases. So know that acids taste sour, right? Like in lemons and vinegar, sour gummies, things like that. Let's see, corn syrup, sugar, starch, beef gelatin, citric acid, malic acid. So these guys, these acids make these gummy worms sour tasting. They're corrosive to metals. So if you put a metal in acid, they can react, and some of them will generate hydrogen gas. They're corrosive to skin, so if you get them on you, you should wash them off. We know acidic solutions turn blue, litmus red, and they can be solids, liquids, or gases. Properties of bases, they taste bitter. Caffeine is kind of an example of that, right? Coffee kind of has a bitter taste. They're also corrosive to skin, and they feel soapy or slippery, right? If you get a little base on you, it feels like soap. It's actually what's happening is it's reacting with your skin to make soap until you wash it all off. Bases react with acids, just like acids react with bases, and bases turn red, litmus, blue. So, right, for litmus paper, acid is red and blue, alu, they said. That was said. All right. Okay, that's enough of there. Acids react with carbonates and bicarbonates to produce carbon dioxide gas. This is just a good reaction to know. So if you take an acid, right, and we remember acids start with H. Here's hydrochloric acid. Reacts with calcium carbonate, which is chalk. What you get is calcium chloride and CO2 and water, right? So this generates carbon dioxide. And you see this reaction mostly in science fair volcanoes, right? You put your baking soda in there with some vinegar, some acid, and then you get some CO2 and bubbles, and it's super exciting. All right, there's 3 definitions of acids and bases, 3 different ways to think about them. The Arrhenius concept of acids and bases, Bronsted-Lowry, and Lewis acids, and we'll talk about this for next semester. Don't worry about it right now. So the Arrhenius concept is that Arrhenius acids ionize an aqueous solution to form hydrogen ions. So if you have something that makes H+, or if we draw H+ with water, what we get is H3O+. So when protons react with water, we call it hydronium. It's just a more correct way to represent protons when they're in water. But for us, they basically mean the same thing. So if you make protons, H+, or you make hydronium ions, H3O+, then you are an Arrhenius acid. So here's some examples. Here's perchloric acid, generates H+, and perchlorate. Right? You'll see H+, if he gets a positive charge, what you know is that the other part of the acid, as it ionizes, must have a negative charge. The other way to draw this, same thing, is perchloric acid plus water gives me hydronium and perchlorate. So by including the water and the proton together, we get hydronium. Arrhenius bases dissociate to give hydroxide ions. So sodium hydroxide will break apart, right, in water to give us sodium ions and hydroxide ions. It's an Arrhenius base. So we can recognize Arrhenius acids and bases in that acids are proton donors or hydronium donors. Bases are hydroxide donors. What about ammonia then, though? It is a weak base. We know this. But how is it going to make hydroxide? It doesn't have one. So to do this, we need a new concept. We're going to use the Bronsted-Lowry concept. And what that is that bases are proton acceptors. So here's ammonia, right? Trigonal pyramidal ammonia with bent water. If ammonia takes a proton away from H, he becomes ammonium ion, right? Tetrahedral. And if H2O loses an H+, it becomes hydroxide, right? So ammonia does generate hydroxide, but by reacting with water. All right, so Bronsted-Lowry acids are substances that donate protons. They can be monoprotic, right? If you donate one proton, like nitric acid, it's monoprotic. Polyprotic means you can donate more than one proton. So H2SO4, sulfuric acid, has 2 protons to give away, so we call it diprotic. So H2SO4 plus water gives me hydrogen sulfate, right, the negative charge, plus hydronium. This guy, though, can ionize again to donate a second proton to become sulfate and H3O+. So 2 protons means diprotic, right? 3 protons means triprotic. So if I have H3PO4, that would be a triprotic acid. Bronsted-Lowry bases, accept protons. So the Bronsted-Lowry concept is that protons either donated by acids or accepted by bases. So here we have hydroxide. If he accepts a proton from water, he becomes water, right? So he's acting as a base. But this is where we see ammonia accepting a proton from water, becoming ammonium. If water, H2O, loses an H plus, now it becomes OH minus. So Bronsted acids, proton donors. Bronsted bases are proton acceptors. Just need to be able to recognize these guys and recognize what monoprotic, polyprotic, right, diprotic, triprotic mean. Another term we need to know is amphoteric. So if you are both an acid, can act as both an acid and a base, you are called amphoteric. So this guy, HPO42 minus, can donate a proton to become PO43 minus. If you donate a proton, you're an acid, right? But he can also accept a proton to become H2PO4 minus. He had one H, now he has two. He accepted a proton from water, making hydroxide. He's acting as a base. So those are amphoteric species. And then finally, neutralization reactions, right? Acid-base reactions. We have acids plus bases. What we say is they make water and a salt. And remember, salts, this sodium chloride is salt, but any salt is an ionic compound, right? Double displacement reaction of an acid and a base. I think that's, the 6 strong acids. I think we've seen this before, but we need to memorize these. So HCl, HBr, HI, these are on the periodic table together, right, under fluorine, bromine, and iodine. Fluorine, don't fall into the trap. He is not. HF is a weak acid. But chloride, hydrochloric acid, hydrobromic acid, hydroiodic acid are strong. And then you have to memorize these 3. Nitric acid, sulfuric acid, and perchloric acid. Hydrochloric, nitric, hydroiodic, perchloric, chloric, and sulfuric. Didn't make it in here. 6 strong bases all have hydroxide, so just recognize lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. The 6 strong acids and 6 strong bases. These show up in questions like, which of the following is a strong acid? We already saw neutralization reactions. Acid plus a base gives me a salt and water. We saw this too, that acids can react with carbonates or bicarbonates to make CO2 gas, right? And this is a critical reaction if you want to have science fair volcanoes. Redox reactions are